let's do some examples. In this video, we're just going to focus on the exponential function. We're going to differentiate and we're going to integrate. Okay, so let's take through this function. E to the 2x divided by e to the negative x plus 2. Think about what you need to do. This is a quotient, so you need the quotient rule. Denominator times the derivative of the numerator, in which I will need the chain rule. Right? That is e to the u times u prime. Same chain rule as before, just new function. Okay, denominator, derivative of the numerator minus numerator, derivative of the denominator. So what's the derivative of e to the negative x? That's a chain rule. E to the negative x, you just rewrite it, leave it alone, multiply by the derivative of the exponent. All divided by the denominator squared. As with most of our chain rule problems, quotient rule problems, we need to clean this thing up. That is ugly. So let's see. Here's the first thing I can do. It's minus minus, make that a plus. And then what should we do? I guess factor out the e to the x. I'm sorry, e to the 2x. What's common? We always want to factor a common factor out, right? That's common. And then let's see what we get after that. So I'm going to factor out e to the 2x and ask myself what's left. This expression times 2. So that's 2 times e to the negative x plus 2. So that's the first one. And then plus, I factor that out, that's e to the negative x. And then the bottom I'm not going to do anything with. And then once I do the factoring, I ask myself, can I simplify what's in here? A lot of times the answer is yes. So let's see. That would be e to the 2x. And this is 2e to the negative x plus 4 plus e to the negative x all over e to the negative x plus 2 quantity squared. And I see these are like terms. 2e to the negative x plus 1e to the negative x is 3e to the negative x. 3e to the negative x. So I can simplify that. And then I think we're good. Okay. Chain rule. So this is, now anytime you see sine squared, I like to rewrite that. Right? The derivative of sine of e to the 3x plus 1 quantity squared. That's like a unique notation for this, for your trig functions, to put the 2 like right here. So I like to put it where we normally put it, that is just outside, indicating we're squaring everything. Okay, so this is going to be a triple chain rule problem, it looks like. But don't worry about that if you don't recognize it. Just do it like one at a time. You notice so I mean, you have this as an input function, it's being squared. And then you have this as an input function of your sine. And then you have this as an input function for your e to the x. So that's kind of confusing. Let's just do it one at a time. Deal with the 2 first. This is my first input function. I treat it as a variable. So 2, leave it alone. Sine e to 3x plus 1. Take 1 away. So that's just a 1. No big deal. And then multiply if you want. You know, if it's going to get confusing, you can just do it like this. Use your chain rule first time. And then multiply by the derivative of the input function, the first input function, which is sine of e to the 3x plus 1. Okay, or you can just take the derivative. If you feel comfortable doing it, just take the derivative. The derivative of that is the cosine. Leave that alone. And then multiply by the derivative of this input function. What's the derivative? E to the 3x plus 1. Well, it's e to the 3x plus 1. You always rewrite that. Times the derivative of the exponent, which is 3. That was a triple chain rule. That's a gotta be careful kind of problem, right? That is a chain rule we had to use over and over again. It's a composite of a composite of a composite. And now I say to myself, can I simplify that? Just be careful with this one, because you're tempted to multiply e to the 3x plus 1 together, but none of them are standalone except this one, right? That's an input to the sine, that's an input to the cosine. I do see a trig identity, but I'm not gonna hold you responsible for that. That would actually clean up kind of nicely. It's like, remember 2 sine x cosine x is the sine of 2x. So this would be clean up kind of nicely. But I'm not gonna. This is calculus. We did our calculus, and I think we're okay with this answer. Just kind of rewrite it like we would. I'll put that guy out first. Oh, 3 times 2 is 6. I can at least do that. 6 e to the 3x plus 1 times sine e to the 3x plus 1 times cosine e to the 3x plus 1. Or, if you're interested, here's a real good way to write it. If you remember this identity, that is 2 sine x cosine x is equal to sine 2x, double angle formula, then you could also write this as just what I have in green here as sine of 2, and then the input is that thing, e to the 3x plus 1 times this thing, 3e to the 3x plus 1. So this one, as you can tell, is a little bit nicer. It's just 2 terms, a sine term and an exponential term. And this one is 3 terms, but both of those are equivalent, and they're both good. All right, now, so we're working with our new function exponential. In the next video, I'll do some log examples. But remember, all this stuff we learned about the derivative is fair game now. So I can ask you, what do we do with derivatives and their applications? We did slope or equation of tangent lines, max and mins where the derivative was 0, intervals of increasing, decreasing, optimization, related rates, implicit differentiation. I'm going to add an implicit. All that stuff, right? All the stuff we've already done is we just have 2 new functions for it. So let's do a tangent line problem. So y prime is, so this is 1/4 e to the x. So the derivative of 1/4 e to the x is 1/4 e to the x, constant multiple rule, minus x, which is 1. And we're interested at the x value 0. This is a x value. It's a little weird the way they wrote it. So when x is 0, I'll use function notation because it looks a little nicer. I get 1/4 minus 1, which is negative 3/4. That's the slope. So now, and you've done a bunch of these by now, y equals mx plus b. And what's b? Well, I know the point is, I guess I could, at the very beginning, I could have done this. It's the input's 0, so I use that for the slope, but I also need the y value on the function itself, right? So what would that be? That would be 1/4 minus 0, right? So that's if I use f of x, then f of 0 would be e to 0 is 1, 1/4 minus, and then put a 0 here, so instead of negative, negative 3/4. Then I get 0, 1/4. And the good news is that's the y-intercept, right? When I plug in 0 for x, 1/4 here, then I can 0 times negative 3/4 is 0, so b is 1/4. So my answer is negative 3/4, x plus 1/4. Okay, all right. As promised, well, we need some more room before we do our integrals. Implicit differentiation. So go ahead and pause the video, see what you get, work it out. Remember, with implicit differentiation, I just take the derivative of both sides with respect to x, and then e to the xy, e to anything is e to that anything times the derivative of the exponent. So what's the derivative of xy? That's the product rule. X, y prime or dy dx plus, then you take the derivative of x, you leave y alone. What's the derivative of the natural log of y with respect to x? Well, it's 1 over y times dy dx. And that should be a minus sign, not an equation, right? Minus, and then derivative 15, 0. All right. And then it's all algebra from here. Yeah, all algebra. So let's do it. X e to the xy dy dx plus y e to the xy minus 1 over y dy dx. That's equal to 0. So what I want to do is solve for dy dx. I got to get rid of this guy first. I'll subtract him over. Let's try and save one step here. So I'm just going to subtract this guy over. Minus y e to the xy. So he's gone. But now he lives over here. Minus y e to the xy. And then everything on the left now has just a has the dy dx term in it, so I can factor it out, which will ultimately allow me to solve for it. Y. And if I factor that out, it leaves me with that minus that. So that's x e to the xy minus 1 over y equals that thing. And then finally, I am done. And we're used to these ugly answers when we do implicit differentiation. And we're done. All right, let's do a couple integrals. So good news here, I don't need u substitution. So I can say antiderivative of the x is e to the x, and then I plug in 0 and ln 2, so I get 1/2 e to the ln 2 minus e to the 0. Inverse property, e to the ln 2 is 2, e to the 0 is 1, 2 minus 1 is 1, 1/2 times 1 is 1/2. Okay, good. Last one, we need u substitution. So I look at that, I say, that looks complicated. So I'm not going to overthink it. I'm just going to do my u substitution. Remember, when we do u sub, it's always u as the input function. The input function. I only got one choice here. Sine x. And then here's my process. Cosine x dx. And then I solve for dx by dividing by cosine x. So dx is cosine x du over cosine x. Okay. Now, almost all the time this works. That is, if I do this u substitution process, if I pick the right u and I sub it in, then I'm going to have a nice, easy integral to integrate. It should just be e to the u. Let's see what we get. So I go e sine x is u. I got a secant x here. I'm going to sub out the dx, which is du over cosine x. And I say, wait a minute, I got a problem. These can't, the x has got to go away. But do you see that connection? Cosine x in the denominator. Well, let's do this one. Remember, secant x is the reciprocal of cosine x, right? So whenever you're multiplying a expression times its reciprocal, you just get 1. So secant x times cosine x, since this is secant x, cosine x times secant x is 1 over cosine x times cosine x, which is just 1. So they cancel out, and that always happens. And then you end up just integrating e to the u or some multiple of e to the u all the time. But you have to do this process in order to figure out what your final solution is. In this case, it just ends up being e to the sine x plus c.